Good day. How you doing, my wonderful students? It's Dr. Manis again. Look, today and this little, hopefully short video, but I tend to ramble. We're going to do the reaction order from a mechanism. Orders in the rate law. It says little exponents M and N in the rate law. Those numbers for M and N, which are usually 0, 1, and 2, most often, 99% of the time, those numbers can only be determined experimentally. So there are 3 experiments we got to go through. Here's the first one. And you get a mechanism. Study organic chemistry, you got tons of mechanisms. A mechanism is just how a reaction happens. Boom, it's 1 step, boom, it's 2 steps, 3 steps, 4 steps, 8 steps. How it actually happens. Okay, typically in general chem, we make 2-step mechanisms. One's going to be a fast step, one's going to be a slow step. The order out of a mechanism is the number of times a reactant. Remember, rate is dependent upon the reactant. So it's the number of times a reactant appears in the slow step. The slow step is really determining the rate. It's kind of like commuting. You have one little tiny slow portion where you go like a mile in half an hour, and that determines how long your commute's going to be. The slow step determines the rate. So here we go with a couple steps. And remember, the overall steps can add up to the overall thing. It should just make sense. The steps for everything adds up to the overall. All right. I have 4 examples to roll with you, and then we'll be good. So, and the first one, let's take a look at this first example right here. Okay. We have 2 steps. Step 1 is the slow step. Step 2 is a fast step. So we're going to pay attention to the slow step. But if you notice, the step 1 adding to step 2 gets you the overall. We have an A and 2 B's, and so we end up with an A and 2 B. Makes sense. How about F and E and C? As I got hiding in there. Well, F appears here, but it gets used up here. So it's kind of like F would be over here as a reactant, F's here as a product. That cancels things out beautifully. So we ignore F. F is what we call an intermediate. Here are products, and so they're written as products. We don't care about C and D so much because we're worried about the rate law. Rate law is written on reactants. So in this one, in the slow step, we have these reactants. A is once, B is once. So the order of A is once, B is 1, and we end up with a rate law, A to the first, B to the first, where those numbers, how many times A and B appear, are orders. And this example over here, we have the slow step, same idea. Slow step is now the second step. Okay. In this slow step, we have reactants F and B. But you say, hey, they're not in the overall reaction. I know they're not. I'm only talking about the slow step. In the overall reaction, if we have to go through it, and I will, okay, on this side, we have an A and 2B. F is again an intermediate, and it's going to drop out. But F being in the slow step will affect what we need to do. So let's look at that. In the slow step, we have F once, B once. And that's what I wrote right here. F is once, B is once. Rate laws cannot be written on intermediates. Rate laws are written on reactants. So somehow we need to get F in terms of reactants. All right, it's not so bad because up ahead, up here, F is made from A and B. So you can go through the algebra with all the pseudo-order rate constants, and that's about a 20-minute video. Not going to do that to you. All I have to really say is, look, if F is an intermediate from A and B, let's sub A and B for F. Okay? So instead of F being once, B being once, the once for F is going to be 1A and then one of those B's, and then tack in that other B. All right? So basically, it's kind of like, if we took these guys right here, A and B, and we wrote them in here for F. Then we got B twice, A once. And so our orders of A are once, B is twice, end up with that beautiful rate law, A to the first, B to the second. But the only reason we could slide that in is up here, there's only one product of F. What if there are 2 products? And that's this groovy little example I got going on for you right here. In this one, we have 2 products. We have the same idea. Here's our slow step, F and B. F's an intermediate. You kind of want to say, hey, I'll sub in A and B for F. Okay? Instead of F, whoops, wrong color there, you know what I'm saying? Instead of F, we're going to write A and B. Well, you can't do that because A and B don't make F. A and B make F and C. So some of A went to F, some went to C, some of B went to F, some went to C. So you can't do that. Again, we can work through the algebra with pseudo-order rate constants over 20 minutes, and I usually only do that for my high school classes when they're being a pain in the bum. But I'm not going to do that to you. All I'm going to say is, look, let's pretend that half of A goes to F, half of A goes to C. So we get half of A, half of B. And I know that's really sloppy there, but it's neater down here. So we're going to sub half of A and half of B for F. So we get half an A, and B will be 1.5, because don't forget this other B right there. So we end up with orders that have fractions in them. The order of A would be a half, B would be 1.5. So that's the 0.02% of the time, 0.1% of the time when the order is not 0, 1, or 2. I saw it in an AP Chem test a couple years ago, so that's what I like to point out to my classes. Usually I don't do that to you on a test because, wow, that'll throw you. But maybe, never know. Anyway, rate equals K, the half, B to the 1/2, basically the same idea except for the intermediate. Just to practice those intermediate things, we have this little setup over here. If you look, intermediates are formed on the right, used up again. They're in the middle. If you want to think about it, the reaction goes in this order. A goes to B, goes over here, and down to there. And so we're talking about things in the middle. I know it's really sloppy. So we got an intermediate here and there. Catalysts, you often are trained from biology. Catalysts increase the rate of the reaction by lowering the activation energy. Awesome. Well, catalysts are also substances that are not consumed by the reaction. That's why they can be reused. So if you look, the catalyst at the beginning disappears and appears at the end unchanged. That's the definition of a catalyst. Well, part of the definition of a catalyst. Up front is unchanged by the reaction, is ready to go. You can just jump right up in there again and go again, ready to rot it again. That's your catalyst. So let's look at a quickie little example down here. In this example, what I have going on here is you got the structure of ozone becoming oxygen. We can add up those two reactions, and you can see that you have two ozones on the left. O is going to be our intermediate. That's what I have written down here to identify the intermediates, because it's being produced and then consumed. So O's are intermediate. If we look at our slow step here, we have ozone and oxygen atoms, I should say, as reactants. Ozone is used once, ozone intermediate. So if we substitute in for O again, we're going to substitute an oxygen in for O. It's kind of like we went, hey, instead of this O, we're going to use another ozone in there. Okay. Actually, it would be half an ozone. Cool. So if you look at this, the ozone would be not to the second power here, but to the 1.5 power there. Again, nothing I would beat you up on a test, but the same idea. All you have to do is find the slow step, number of times the reactants appear in the slow step. If you have an intermediate, you sub for it. Not a big deal. Hopefully you learned a little bit. We're going to need to practice things later. I imagine your teacher will do this again and again in class. Have a good time. Learn it like it.